No, that was A3, sorry. A population mean. Mu. Mu, is that look like a mu? That's something. Alright, so averages. Averages, and you have to be given a sample, of course, of size n with sample mean. Sometimes they won't use the word sample again, right? They might just say with mean, and then they give you the mean. That's x bar. And then either your sample standard deviation, which is the more common situation, S, or they might tell you the population standard deviation, sigma. Right, this is the more common situation where you actually just have the sample standard deviation together with the sample mean and the sample size. And in that case, we're going to use t-test, because there's a t-distribution that models the sampling distribution in that case. If you're given the population standard deviation sigma, then you can use z-test, because in that case, you can actually use the normal distribution. But in each case, just like last time, you're going to set up HO and H1, your null hypothesis and your alternate hypothesis. Remember that the null hypothesis always has equality. The alternate hypothesis is going to either be not equal, less than, or greater than. We have to look at which one's your claim based on the wording of the claim. So usually I'll say, write the claim in symbols first, identify which one it is, and then what the other one is. So maybe this is while you do this. Wash's board too. It came out really bad in the video, if anyone looked at the video. We'll do that at break. Alright, so you set up your hypotheses, and then you identify your sample statistics, what you're given. Sample stats. And you go to your calculator and have your calculator calculate the test statistic, which is usually going to be a t-score. Sometimes it's a z-score. And the p-value, which it just calls p. Then you compare your p-value to alpha, which is also going to be given, so you have to look for it. They'll tell you what to use for alpha. Remember, it's usually 0.05. Sometimes it's 0.01. So then, you make your conclusion about the null hypothesis first, right? Because the null hypothesis, HO, is your kind of your underlying assumption, what you're assuming is true. And then you do this calculation, underlying assumption. You do this calculation, and if it's really small, what that tells you is that it would be really unlikely to get those sample statistics under the assumption that the null hypothesis is true. And so if it's really unlikely, like too unlikely, like smaller than alpha, then we say, whoa, that shouldn't have happened, reject the null hypothesis. So if the p-value is less than alpha, reject HO. And then since HO and H1 are opposites in some sense, we would then say we support H1, the alternate hypothesis. Of course, if the p-value is not less than alpha, which was the case in I think every single test we did last time, if the p-value is greater than alpha, then you fail to reject the null hypothesis. Basically, it's not extreme enough. That could happen. We don't really know. It's kind of inconclusive. And so we also, or I'll say you also, fail to support the alternate. That's again when there's not enough evidence, or not sufficient evidence. Right? When the p-value is less than alpha, there is enough evidence. So then the final step is towards your conclusion. State the final formal conclusion, however you want to say it. They'll just say what's your conclusion. Where you say at alpha equal whatever you're using for alpha, at that level of significance, either there is or is not enough evidence. And then that's going to be either to reject or support the claim based on whether the claim is the null hypothesis or the alternate hypothesis. And then just restate the claim in words. Yakka, yakka, yakka. So, while you finish copying that down, let me pull up the PowerPoint. Maybe I'll pull up an actual exercise first, and then we'll go through the PowerPoint. Number one, somebody's question number one from 8-4.
So what's the difference in this and what we did Friday?
The only difference is that now we're talking about a mean instead of a proportion. And so you're going to be given n, x bar, and s or sigma instead of p hat and n. Very, very similar. Yeah, it's really just different statistics, and it's about an average as opposed to a proportion. So almost identical, really. That's the good news. So, and then the next section is the same as well, except for we're going to be comparing two means, and so we're going to have two sets of sample data. But it's still just a matter of plugging it into your calculator and making the right conclusions. Alright, so this one says, assume that a simple random sample has been selected from a normally distributed population. Those are the things that have to happen to make this work. Test the given claim. Identify the null and alternative hypothesis. They use alternative. I've always heard it as alternate, but same thing. Test the test statistic p-value and state the final conclusion that addresses the claim. Alright, in a manual on how to have a number one song, it is stated that a song must be no longer than 210 seconds. A simple random sample of 40 current hit songs results in a mean length of 241.3 seconds and a standard deviation of 55.31 seconds. Alright, so they're giving you information about the sample, right? Use a 0.05 significance level and the accompanying Minitab display, although you don't need that. I don't know why they do that. Unless they are identifying stuff for you. What is this? Have you looked at it? They are just identifying this stuff. That's for people actually who use Minitab. They will plug in their data into Minitab and it spits out that stuff. So we don't need that, but we've got all that we need in the problem. Test the claim that the sample is from a population of songs with a mean greater than 210 seconds. What do these results suggest? Alright. So, we start off with identifying the claim, identifying the sample data. Right, let's write down the sample data first. And then let's write down everything that's given, right? Sample data, sample statistics are a sample size N of 40 hit songs with a mean length, that would be X bar, of 241.3 seconds with a standard deviation, so that's S because it comes from the sample, 55.31. We're going to use alpha equal 0.05 to test the claim that, yep, comes from population songs with mean greater than 210. Mean greater than 210, that's population mean. So in symbols, that's mu is greater than 210. So that has to be which one? Alternate hypothesis or null hypothesis? Alternate. Because the null hypothesis, HO, always has to be equals. So we've got an equals versus greater than situation. Equals versus greater than. They always write HO first, but I like to write the claim first. Alright, you want to focus on which one is the claim for the wording of your conclusion. Since our claim is H1, we're going to be able to use the word support in the conclusion. Alright, so then we go to the calculator, and what are we using in the calculator for this one?
Z-score. No, Z-test.
T-test. T, because we're given the sample standard deviation, right? If you're given S, you use T-test. Just like for confidence intervals, you would use T-interval in that case. Given sigma is when you use T-test. So we're going to use T-test, and that's most of the time. All right, so let me pull up the calculator. All right, go to the screen. Stat. Test. T-test is number 2. Alright, make sure stats is highlighted. This is probably new. When you first open this up, you probably had a display that looks like that, where it's got data highlighted. And this gives you the option, if you want, to actually put data into a list and then have your calculator calculate the summary statistics. But we are given the summary statistics. We are given X bar, S, and M. So we go over to stats, hit enter to highlight it, so that it will ask for what you have. Okay? Now first of all, mu sub 0, just like p sub 0 in the testing about a proportion, that's the mean in the claim and in the null hypothesis. So that's 210 in this case. That's what we call the hypothesized mean. That's what we're assuming it is for the purposes of calculation. And then X bar is 41.3. What's S? 55.31. N? 40. And which one is our alternate hypothesis? Is it greater than? So that tells it that this is what's called a right-tailed test, and it's supposed to calculate the p-value to the right. So we go down to calculate and hit enter. Alright, and then it restates the alternate hypothesis and then gives you your test statistic and your p-value, and then it restates your sample statistics. So the test statistic, T, is 3.579, which is pretty extreme. That means it's more than 3 standard deviations above the mean. And the p-value, what's the p-value? Be careful. Is it 4.7? No.
Oh.
It's 4.7 times 10 to the negative 4. That can't be 4.7 because it's a probability. So look for that. If you see a number that's bigger than 1 initially, go, ooh, that can't be, must be scientific notation.
0.005.
Good, 0.000.
5.
Yeah, let me write 47, because if they want 3 decimal places, you'd actually want to round it down to 0. So let's see, in this homework question, what they want. They want 2 decimal places for the t-score, test statistic. Yeah, so this one, sure enough,
Okay.
rounding to 3 decimal places, you look at that next digit, which is a 4 initially, to round down. So it's negligible, essentially 0, rounds down to 0 anyway. So that's definitely less than alpha. Alright, they said alpha was 0.05, but even if it were 0.01, this would be a really small extreme p-value, so that means we reject the null hypothesis and support the alternate hypothesis. So then the conclusion is at alpha equal 0.05, or like I said, really any alpha in this case, but that's what they told us to use. There, what is enough evidence, because we're in this extreme conclusive situation, to do what? Support the claim, because our claim is H1. Support the claim that the population mean, or we could just say mean, but it's the population, the mean of all songs is greater than 210 seconds. So then, as far as answering the thought question, what do the results suggest about the advice? The advice was that the song must be no longer than 210 seconds, but these are hit songs, and their average is greater than 210 seconds, so I don't think their advice is good, yeah. 210, no longer than 210 seconds is not song advice, these are hit songs, they're longer. Alright, any questions on that?
When it says significant level, is that referring to
Alpha.
alpha two?
Yep, sure is. Alright, so let me pull up the PowerPoint for A4. Stream of claim about a mean. So, they say the first part is when sigma is not known, that's when we use t-test, and the second part does talk about when sigma is known, which is z-test. They work the same way otherwise. T-test is the t-distribution, there's notation. Again, there are certain requirements that will be met, you don't have to check those. Here's the lovely formula that's built into your t-test to calculate this test statistic. Incorporates the sample mean. This is actually the hypothesized mean. Mu sub 0 should be the subscript there. Well, it's the mean of the sample means also. And then S is your sample standard deviation. So all these things come into play as to figuring out where our sample lies on the sampling distribution. And they go through the t-distribution again. Here's another example. This one they actually give the data, so you could put that into your list and do it with the list option, but they also calculated the summary statistics, so might as well just use those. This one says we've got some radiation emissions in wickages, watts per kilogram, that correspond to a sample of cell phones. They want you to use 0.05 for alpha to test the claim that cell phones have a mean radiation level that is less than 1.0. Alright, so let's start over with this one. Again, you've got some sample data. What's n in this case?
11.
Good. How'd you get that?
The number.
How many data values? You actually have to count. They didn't do that for you, but if you count how many numbers there are 11 of them. And then X bar, they did give us 0.938, and S, they gave us 0.423. And here we're testing the claim that the mean is less than 1.00.
So that's eight, is that eight
H1
one?
again, yep, because HO is always
Yeah.
equality. Use equal 1.0. There. Alright, so that's what you want to pick out. They also check the requirements. Again, you won't have to do that, just assume it's gonna work, otherwise you can't do the problem. And so sure enough, they write the null hypothesis first as the one that's where it's equals, and then the alternate hypothesis, in this case it's the claim that it's less than. They note the significance level and that it's about a mean, and so it's gonna be a t-test. This is where behind the scenes they would, calculate the t-score. Calculator's gonna do this for you, of course. And here's the screen, and this actually now should be in your handout if you want to pull that out if you haven't already. Who are we on? So we did one prop z-test last time on page 7. And now let's see, page 9, it starts page 10. So there's this example and then the screenshot that shows how you've got to go to t-test, make sure your stats is highlighted, put in your 1 or 1.00, your sample mean, your sample standard deviation, your sample size, and select less than. And then if you go down to calculate, you get the calculations. Or if you go to draw, you get the picture. And so the t-score here, sure enough, is negative 0.486. That says we're less than half a standard deviation below the mean. So you see, that's not very far. And you can see that in this picture too. That's not very far to the left. So that's going to be the inclusive situation. The p-value is a 31% or 32% chance of getting this sample data under the assumption that the null hypothesis is true. So it's probably true, we don't really know. We cannot, or we fail to reject it. So we fail to reject the null hypothesis, so we fail to or cannot support H1. So, conclusion here is at alpha equal whatever we're using, 0.05. Right, this is bigger than 0.05. Again, it would be bigger than just about anything we would use for alpha. Alpha is really only significant when it's close, right? If it were 0.06 or 0.02, then we'd have to say, oh, what are we using for alpha? Let's double check this. But when you have a big p-value, it's for sure going to be bigger. If you have a really small p-value, it's for sure less. But anyway, we want to restate alpha and then say in this case that there is not enough evidence to do what? Our claim is H1, so to support the claim. So again, the not enough evidence is because the p-value is bigger than alpha. And support, using the word support instead of reject, is because the claim is H1. And then we restate the claim that the mean is less than 1.0. Look at this. Alright, this one is also in your textbook if you want to refer to screenshots and a little bit more explanation, pages 427 to 429. They go in a little bit more detail. Screenshots with the calculator that has color, they actually let you choose a color on some of those calculators for your drawing. Cell phone radiation, the p-value method. I'll even do some quartile plots, we're not gonna do that. there's also this idea that I think I mentioned last time of how you can compare the test statistic with something called a critical value. And this is not gonna be on your test, but it is in one of your homework problems. All right, there's this idea that in this case we've got a test statistic of negative 0.486, right? That's not very far from the middle, and the p-value is this area here, like the calculator drew. That p-value is the 0.3187. That's that area from there on down. It's like the probability of being that extreme or more so. You know what to call it. Now that, comparing that p-value to alpha, we concluded that there's not enough evidence. That's because in this case, alpha is a smaller area. Alpha is 0.05. And that's what we're using for too extreme or too unlikely. Well, alpha has its own cutoff here. That's a t-score. And that's called the critical value. Again, a t-score in this case, because it's a t-distribution, sometimes it's a z-score. And we looked at how you can calculate z-scores with the inverse norm, right? Because z-scores come from the standard normal distribution. So if you did inverse norm of 0.05, you would get the z-score. But here we want a t-score, and not all of our calculators do that for us. So there's a table that you can use. And I want to show you a problem where that's basically what we're going to do to compare this cutoff with that test statistic to see if it's in what we call sometimes the critical region or the rejection region. Because if this test statistic is beyond the critical region, critical value, that would be the same thing as the p-value being smaller than alpha. In this case, the p-value is bigger than alpha. The test statistic is not beyond the critical value, is it? Right? Critical value is here. The cutoff for alpha is here. We're over here. P-value is bigger than alpha. But if it were the reverse, if this test statistic were out here, then the p-value would be smaller than alpha, and the test statistic would be beyond the critical value. That's another way of making the same decision. So let me show you the homework problem that's like that. One of my students in my other class always sent it to me saying, how do I get a critical value? So, and like I said, this is not gonna be on the test, this is just to expose you of this other method.
Is it gonna be on file?
No, we're all just using the p-value approach because it's just as good. But this is another way of drawing the same conclusion. Bless you. So I'll show you the p-value method in this case too. This one is IQ scores of statistics professors. So the claim here is that the mean IQ score of statistics professors is less than 118, which of course we know is not true. It's much greater, right? We'll see. All right, so the claim is that the mean IQ of stats profs is less than 180. In other words, mu is less than 180. And so we've got a H1 claim. HO would be that it's equal. I would claim this actually greater, but that's just me.
I know on the homework the HO is always on top.
Yeah, that doesn't matter.
Okay.
I was saying I like to put H1 on top when it's the claim, but they can go in either order. All right, so we've got an equals versus less than situation. This person picked that out correctly. And we've got some sample statistics, our sample data that's given is n equal 23, x bar equal 113, and s equal 10. Alright, so first it asks for the test statistics. So you go to your calculator, t-test, and I'm going to write down the p-value as well, although this one doesn't ask for that. So stat, test, t-test, Alright, so, go ahead and just calculate, I get a t-score of negative 2.398. And a p-value of 0.013. Alright, so, homework problem says, oops, there's our test statistic. Now they want you to get the critical value. So there's this table, which means it's not too hard to do. The table talks about where you have area in one tail or area in two tails. Now to do that, you want to look at what situation we're in as far as really as far as the alternate hypothesis. Do you remember last time I kind of showed you that if it's equals versus not equals, it's what we call a two-tailed test, where if you're too far in either direction, then we reject the null hypothesis. Whereas if it's like this one right here, this less than situation, that would be less than versus equals, or equals versus less than. And then the greater than situation would be a right-tailed test. So that's how your calculator is calculating the p-value in either both directions or the left or the right. So if it's less than or greater than, it's what we call a one-tailed test, either right-tailed or left-tailed. Whereas if it's equals versus not equal, it's the two-tailed test. So that's what this is talking about. Do we want the area in one tail or in two tails? Is it greater than or less than, or is it equals versus not equals? It's greater than or less than. So area in the one tail. And then the degrees of freedom, this in a t-test is one less than the sample size. You just have to remember that. N minus one for the table. So that's what we're looking at here. So they said to use alpha equal what in this problem? I missed it. Close that up again. Alpha. Thank you. Where is it?
Okay.
At the top. Blah, blah, blah. Oh, right there, finally. Alpha equal 0.05. I have to search for it so much. Alright, so when you go to the table, you're looking for alpha equal 0.05, one tail. So that is this column right here. Okay? And then degrees of freedom, how big is our sample? 23. What's one less than that? 22. So we go that column and that row, and we've got 1.717. So the critical value is 1.717. Well, that's if we're to the right, if it's a right-tailed test. This one is a left-tailed test. So we want negative. Because we're going to reject HO if we're too far to the left for this one. And so the critical value has to be a value on the left. If the right-tailed test greater than, it's to the right. If it's a two-tailed test, guess what? You get both of them, plus and minus. So there's a reason why we're not using this method. Alright, comparing the p-value to alpha is way simpler. But this works, So the picture for this one is we have basically a hypothesized mean of 118. The sample mean was 113. The question is, how far is 113 from the mean? In terms of z-scores, or t-scores, it's negative 2.398. Now, is that too far to the left? Well, the p-value is the area beyond that, which is 0.013. And how does that compare to alpha? Yeah, so alpha is 0.05, right? So
It's
alpha is
less than.
bigger. So in fact, this should be further to the end than I drew them. So it's less than alpha, so we can tell just by the fact that the p-value is less than alpha that we should reject HO. It's too small to believe, reject HO.
Is this another way?
Right. The other way to do it is to compare this cutoff for alpha, which which is the negative 1.717, to compare t-scores. To say, oh, our test statistic is beyond the critical value. Right, this is the t-score, the test statistic, it's more than 2 standard deviations to the left of the mean, right, I should have drawn it further out. And the cutoff for what's too unlikely is beyond negative 1.717, that's what the critical value tells us. So it's just another way of making the same decision that it's too extreme, reject HO, support H1. It's just comparing numbers on the number line as opposed to areas. Alright, so back to the PowerPoint, let's finish this and I'll give you a break. This just goes on to the situation when sigma is known. If sigma is known, you get to use the z-scores instead of t-scores, otherwise it works the same way. Very similar formulas built into your z-test. This one just says, what about if we said sigma was 0.480, right? If they use that symbol, that's when you use z-test. This one comes out pretty much the same as z-score that's not that small, and there's the end of the thing. So, p-value again. Anyway, just that one problem, see if we can figure out the t-score, the critical value. In this case, I think he put the positive instead of the negative was all that he did wrong. And then the conclusion you should be able to get just as easy. So, let's take a break and then we'll do comparing to these.